Hello students, in the last lecture we discussed the basics of random process. We showed that a wide sense stationary random process WSS random process can be characterized in terms of its mean mu x and the autocorrelation function Rx of m. We also showed the importance of power spectral density and how power spectral density is related with autocorrelation function. In this lecture, we discussed about linear invariant systems with random inputs. Why a linear model? In many applications, physical systems are modeled as linear time invariant systems. We will discuss what is Lti system. Such a linear system is called a linear filter in signal processing. So, filter and system they are used interchangeably in this course. Finding a linear filter that can optimally estimate a signal from the observed noisy data is an objective of SSP. The observed data and the signal are correlated. That is one important observation, that observed data and the signal are correlated. This correlation is exploited in optimal filtering. So, one application of linear filter is optimal filtering, which exploits the correlation between observed data and the unknown signal. Many WSS signals are represented by linear models. We will discuss about those linear models. The linear system theories plays an important role in these models. In this lecture, we will introduce the basic techniques to analyze the response of an Lti system to WSS random process as an input. First, I will introduce the Lti basics. A system is modeled by a transformation T that maps an input signal xn to an output signal yn, and we write yn is equal to T of xn. Thus, if xn is the input, the system is modeled by a transformation T and yn is equal to T of xn is the output. So, we know what is a system. System is basically modeled by a transform. Now, linear system. The system is called linear if superposition principle applies. What does it mean? The weighted sum of inputs results in the weighted sum of the corresponding outputs. So, in terms of transformation, this is the weighted sum T of A1 x1 n plus A2 x2 n is same as A1 times T of x1 n plus A2 times T of x2 n. So, this is the weighted sum of the output. A1 times output due to x1 n plus A2 times output due to x2 n. So, we saw what is a linear system. Now, time invariant system. This system yn is equal to T of xn is called time invariant if T of x of n minus n naught is same as y n minus n naught. So, if we have the delayed input, then the corresponding response will be also delayed. So, this is the time invariant system. Another important concept is causal system. The system yn is equal to T of xn is called causal if yn depends on the present and the past inputs only. So, it does not depend on the future data. So, that way yn is a function of xn, xn minus 1 etc. We will be dealing with linear time invariant causal systems. This is very important. We will discuss Lti causal systems. Impulse response of a system. Now, a linear system is characterized by its impulse response. So, we will see what is an impulse response of a system. An Lti system can be characterized by its impulse response Hn, it is denoted by Hn, is equal to transform of delta n. So, output due to impulse, where delta n is the unit impulse. In signal processing, it is defined as delta n is equal to 1 for n is equal to 0, 0 otherwise. It is an only at n is equal to 0 there is an input. So, that way suppose if this is my n axis, then suppose this is n is equal to 0, 1 etc. So, at n is equal to 0 the value of the signal is 1 and elsewhere it is 0. So, that way, so this is the impulse signal. Now, impulse response is the response due to impulse. So, here suppose there is an Lti system, your input is delta n and corresponding output is called the impulse response and it is denoted by Hn. Now, for a causal system, Hn is equal to 0 for n less than 0, because your delta n is non-zero only at n is equal to 0. Therefore, for n less than 0, Hn must be equal to 0 for a causal system. Depending on the duration for which Hn is non-zero, finite impulse response FIR and infinite impulse response IR systems are defined. We will call suppose an FIR system for which impulse response is of finite duration and IR system for which impulse response is of infinite duration. Now, how to get the output of an Lti system? Any signal Xn can be represented in terms of delta n as follows. That is, Xn is summation xk into delta n minus k, k going from minus infinity to plus infinity. Because we see that when we put k is equal to n, here it will become n minus n 0, then it will be delta 0 is equal to 1, and for so when it is xn, that means this one will be delta 0, that is equal to 1. Therefore, it will be the right hand side will be xn only. For remaining values of n, delta n minus k will become 0. So, that way xn can be represented in terms of this infinite sum. Now, what will be the yn? Yn will be transformation of xn, that is equal to transformation of this sum. Now, we see that xk is a constant, it is not a function of n. So, therefore, we can write t here. So, this summation will be xk into t times delta n minus k, and t of delta n minus k, that is the response due to delayed impulse, is denoted by h of nk. Therefore, yn for a linear system will be summation xk into h nk, k going from minus infinity to plus infinity. So, as I said, this h n k is the response at time n due to this shifted impulse delta n minus k, h of n k. This is the response at instant n due to the impulse at n minus k. Now, suppose the system is time invariant, the linear system is time invariant. In that case, because the output due to the delayed impulse will be just delayed impulse response. So, that way h of n k is equal to h of n minus k for a time invariant system. So, in that case we can write yn is equal to summation xk into h of n minus k, k going from minus infinity to infinity, and this is the convolution operation. Therefore, we can write xn star hn, star is the convolution operation. So, what we have seen, if the system is time invariant, system is linear and time invariant, in that case yn, output yn can be expressed as the convolution of xn, input xn, and the impulse response hn, convolution of xn and hn. Thus, if yn is the output of an LTI system with an impulse response hn to deterministic input xn, yn is the output of the LTI system to deterministic input xn, then yn is equal to, in the previous expression we showed that it is summation xk into h sub n minus k, k going from minus infinity to infinity. Now, noting that convolution is a commutative operation, we can write this as summation hk into x sub n minus k, k going from minus infinity to infinity. So, this is the output of an LTI system to a deterministic input xn. Now, in terms of filter terminology, these hk's are called filter coefficients. For a causal filter, if we assume that the filter is causal, which is realizable, Sk is equal to 0 for k less than 0. So, in that case we can write, suppose for a causal IIR filter, yn will be equal to summation Sk into x of n minus k, k going from 0 to infinity. So, if we put Sk is equal to 0 for k less than 0, we get this result. For a finite impulse response FIR filter, Sk is 0 for k greater than equal to m for some constant m. So, therefore, for a causal FIR filter, we can write yn is equal to summation Sk into x of n minus k, k going from 0 to m minus 1. So, that way we have seen how to represent the output of a linear time invariant system in terms of the input and the impulse response of the system. Now, let us see how we can represent the same result in the frequency domain. We have yn is equal to xn star hn, where hn is the impulse response, which may be finite duration or infinite duration. Taking the Dpt, because it is a discrete time signal, we take the discrete time Fourier transform. Taking the Dtft, we get y omega, that is Fourier transform of yn, discrete time Fourier transform of yn is equal to, it is convolution in time domain, therefore, in frequency domain it will be multiplication, that is h omega into x omega, where h omega is the Dtft of hn, and we can write it as summation hn into e to the power minus j omega n going from minus infinity to plus infinity. So, this is the Dtft of hn sequence, and this term in system theory we call the frequency response of the system. H omega is the frequency response of the system. Therefore, discrete time Fourier transform of the output is equal to frequency response multiplied by the discrete time Fourier transform of the input. So, if we write in terms of z transform, this will be yz is equal to hz into xz. In fact, if we put z is equal to e to the power j omega, we will get this expression, where hz is the z transform of hn, and this is the expression summation hn into z to the power minus n going from minus infinity to plus infinity. And hz in system theory is called the transfer function of the system. For a discrete time system, hz is the transfer function. Now, we have the background of the linear time invariant system. Let us discuss the response of an LTI system of impulse response hn to a WSS input xn. So, impulse response is hn, and input xn is WSS, that we assume. Now, you know that the WSS process xn is characterized by mean mu x, that is E of xn, and autocorrelation function Rx of m, that is E of xn into x of n plus m. And also we can characterize, because autocorrelation function has the Fourier transform power spectral density, therefore, we can also characterize the WSS process in terms of power spectral density Sx omega, PSD Ss omega. So, these are the quantities which characterize a WSS random process, mean mu x, autocorrelation Rx of m, and PSD Sx omega. Now, input is a WSS signal. What about the output? So, we will prove the white sense stationarity of the output. We have yn is equal to xn convolved with hn, that is equal to summation hk x of n minus k, k going from minus infinity to plus infinity. Let us take expectations of both sides, then E of yn will be E of this sum. This is the expectation of some weighted sum, and this we can write as summation k going from infinity to plus infinity hk into E of x of n minus k, because hk is a constant random variable. So, therefore, expectation operation will come here, and this we can write E of yn will be equal to summation hk into mu x, because this quantity is constant at every time point. Therefore, we can write it as mu x, that is it, as xn is a WSS process, this quantity will be mu x. So, what we conclude, E of yn is equal to mu x we are taking out, into summation of hk, k going from minus infinity to plus infinity. This quantity is the frequency response at 0 frequency or 0 frequency gain. How? Because we can write, suppose we have h omega is equal to summation hn into e to the power minus j omega n, n going from minus infinity to plus infinity. Now, we will put omega is equal to 0, h 0 will be equal to summation hn e to the power minus j 0 into n, and that will be 1, n going from minus infinity to plus infinity, that is equal to summation hn n going from minus infinity to plus infinity. So, that way E of yn is equal to mu x into h of 0. What does it mean? That E of yn is a constant now, this is a constant, and this quantity is a constant. So, this is one of the requirement for WSS process, that process should have constant mean, and we have seen that yn has constant mean. We will continue about white sense stationary of the output. Let us see what happened to the cross correlation function, E of xn into yn plus m, that is equal to E of xn into and y of n plus m, that is the summation or convolution of hn and yn plus m. So, that we can write as summation hk into x of n plus m minus k, k going from minus infinity to plus infinity. Now, we can take E inside, because these are a constant quantity. So, E of xn into x of n plus m minus k. Now, using the WSS concept, this quantity will be a function of the lag n plus m minus k minus n, that is the lag, that is equal to m minus k. Therefore, this cross correlation function is equal to summation hk into Rx of m minus k, k going from minus infinity to plus infinity. So, we see that this is a function of lag only, it does not depend on n. Therefore, we can write Rxym, that is the cross correlation function at lag m, is equal to Rx of m convolved with h of m. Similarly, we can write E of yn into yn plus m is equal to h of minus m convolved with Rxy of m. So, here again if we substitute yn is equal to summation hk x of n minus k, k going from minus infinity to plus infinity, then we will get this result. So, here again we will see that it is a function of lag m only. We can write Rym, that is output autocorrelation function, is equal to h of minus m convolved with Rxy m, and from this result we will write this equal to h of minus m convolved with hm convolved with Rx of m. So, this is the output autocorrelation function. And what we conclude? We conclude that if yn is the response of an Lti system of impulse response Hn to WSS input Xn, then Xn and Yn are jointly WSS, because output Yn is a WSS process, Xn is a WSS process, and their cross correlation depends only on lag. Therefore, Xn and Yn are jointly WSS. And second conclusion is that mu y is equal to mu x into H0, where H0 is the zero frequency gain or DC gain, and Rym is the convolution of Hm, H of minus m and Rx of m. So, these are the results we established. This is the characterization in time domain. So, these are characterization in the time domain. In the frequency domain, we will see what happened. Power spectrum of the output. We have Rym is equal to h of minus m star h of m star Rx of m. Now, again we will take the DTFT. So, DTFT of Rym is Sy omega. So, that will be equal to, now h of minus m, if we take the DTFT, that will be h omega star, complex conjugate of h omega, into h omega into Sx of omega, PSD of Xn. So, because convolution in time domain will be multiplication in the frequency domain, we get this result. Now, h star omega into h omega, that is mod of h omega square. Therefore, Sy omega will be equal to mod of h omega square into Sx of omega. So, this is the relationship between PSD of the output and PSD of the input. Thus, the spectral properties of a WSS signal can be modified. This is modified because this function is multiplying Sx omega. So, Sx omega will be now modified, can be modified by passing it through a linear filter. So, this power spectrum we can also express in terms of Z transform. So, that Syz will be equal to Hz inverse, Z transform of this will be Hz inverse into Hz into Sx of Z. This Syz is the generalized PSD of the output process, Sxz is the generalized PSD of the input process. We will consider one example. A discrete time WSS process Xn with mu x is equal to 0 and the autocorrelation function Rxm, which is equal to 1 at m is equal to 0 and 0 otherwise, is input to an FIR filter with filter coefficient Hn is equal to 1 for n is equal to 0 and n is equal to 1 and 0 otherwise. This is a two-step filter, only two values, at H0 is equal to 1 and H1 is also equal to 1. Find the mean, the PSD and the autocorrelation function of the output process. we will find the solution here. The frequency response of the system, because this is the impulse response, we have to take the DTFT. So, frequency response of the filter is given by summation Hn e to the power minus j omega n going from minus infinity to plus infinity. But here for all other values of n, Hn is equal to 0, only at n is equal to 0 and 1 we will get Hn is equal to 1. Therefore, we will have this is H0, that is 1 into e to the power j omega 0, that will be equal to 1, plus H1, that is 1 into e to the power minus j omega into 1, that is e to the power minus j omega. So, that way H omega will be 1 plus e to the power minus j omega. Once we know H omega, we can find out the output mean, and that is equal to mu y into mu x into h sub 0, and we know that mu x is equal to 0, therefore, this will be equal to 0. So, therefore, output of this filter is 0 mean. Now, we have to find out the output power spectral density. Before that, we have to find out what is input power spectral density, that is Sx of omega is equal to summation Rx of m into e to the power minus j omega m going from minus infinity to infinity. So, here only one value of Rx of m is non-zero, that is at m is equal to 0 it is 1, otherwise it is 0. Therefore, it will be equal to Rx of 0 into e to the power minus j omega 0, that is equal to 1. For omega, anyway, power spectral density is uniquely defined, because it is a discrete time Fourier transform, it is uniquely defined in a period from minus pi to pi. So, that way Sx omega is equal to 1 for mod of omega less than equal to pi. Now, we can find out the output PSD. So, the output PSD is given by Sy omega, that is equal to mod of h omega square into Hx omega, and we know Hx omega is equal to 1, therefore, 1 into 1 plus h omega is 1 plus e to the power minus j omega mod of 1 plus e to the power minus j omega square, and this we can write as if we expand it, we will get it as 2 plus 2 cos omega, for mod of omega is less than equal to pi, because DTFT is uniquely defined in a period from minus pi to pi. And this cos omega again we write in terms of e to the power j omega plus e to the power minus j omega, so that we can now compare with this expression Sy omega is equal to summation Rx m e to the power minus j omega m going from minus infinity to plus infinity. Here we see that only 3 terms are there corresponding to omega is equal to 0, omega is equal to minus 1 and omega is equal to plus 1. So, therefore, corresponding coefficient will be the autocorrelation function. Therefore, by inspection Ry of 0 will be equal to 2, Ry of minus 1 will be equal to Ry of 1 will be equal to 1, and for rest of the values of m, Rym will be equal to 0. Let us summarize what we have learned today. For an Lti system with impulse response Hn and input Xn, the output is given by this convolution relation Xn convolve with Hn, and if we expand, that will be equal to k summation Hk into x of n minus k, k going from minus infinity to plus infinity. This is the output of a linear time invariant system due to an input Xn. Now, if the system is causal, in that case Hk is equal to 0 for k less than 0. Therefore, Yn will be equal to summation Hk x of n minus k, k going from 0 to infinity. In the transform domain, we have y omega is equal to h omega into x omega. This is by taking the DTFT we get this relationship, and this h omega is the dTft of Hn is known as the frequency response of the system. And similarly, we can write in Z transform domain Yz is equal to Hz into Xz, and where transfer function Hz is equal to Z transform of Hn. Coming to the random process, a WSS process Xn is characterized by its mean mu x and the autocorrelation function Rx of m. So, WSS process Xn is represented by its mean mu x and the autocorrelation function Rx of m. Also, the PSD Sx of omega. For an Lti system with impulse response Hn and WSS input Xn, input Xn and output Yn are jointly WSS, that we established. Then mu y, that is mean of the output process, is equal to mean of the input process multiplied by H0, where H0 is the DC gain of the system or zero frequency gain of the system. The autocorrelation function of the output process Rym is given by Hm convolved with H of minus m convolved with Rx of m. It is the convolution of Hm, H minus m and Rx of m. And in the frequency domain, we get Sy omega is equal to mod of H omega square into Sx of omega. Also, in terms of Z transform, Syz, that is the generalized PSD, is equal to Hz inverse into Sx of Z. Thank you.